All right, on to Resnet. So Resnet stands for residual network. We're going to come back to this word in a bit. Let me first provide you the intuition for how a ResNet works. So if we think about taking our input and feeding it into various layers and going into our output, we see that it can be difficult, once we compute our loss, to push gradient all the way back here, right? Because if we've got the first layer, we have to be, in order to get the gradient back here and calculate the gradient, we take our loss, we calculate the derivative of the loss with respect to this layer, and then go to the previous layer, previous layer, previous layer, previous layer, previous layer, and these are all both multiplying by the weight matrices all the way back here, and they're also multiplying by the derivative of the activations. So when we have this long chain of all those, it's very easy to have either exploding gradient, which we can deal with gradient clipping, or vanishing gradient, which we don't have a good solution for. Let's come up with a good solution though. Let us say, pictorially, let's say we could do something like this, where we could optionally route around a particular layer here. And I'm going to call this a skip connection. And so we will provide this idea, where we can skip around any layer. Okay? How that's done, we'll talk about in a moment. But for now, what I want you to know is, in this skipping, we're going to ensure that the derivative of the skipping is going to be 1. So that means when we are trying to push back a gradient, there will be, if we want to go to this first layer, lots and lots of different paths that we can get to here. We can come directly through, like we used to, going back through every layer. But there's another alternative. We could choose to take the express train and take all the skip connections. If we take all the skip connections, lo and behold, back to here, we have got gradient that's just multiplied by 1 the whole way until we get back to here. So we've got a full helping of gradient that's coming back to this connection here. We've got actually more than just that path, right? We've got this path that takes the skip connection all the way. We've also got another path that takes the skip connection all the way up to before the last layer. So now we go through the layer here using the weight matrix, and then gets us to the connection. Or we might have chosen to go all the way to the skip connection to here and then go 2 layers. Or to here, go through this layer here and then take a skip out. So in fact, we have 2 to the n different such paths that'll take us back here, where we're choosing at every point to take a skip connection or not take a skip connection. Okay, we don't have to worry about those 2 to the n. Again, we're going to use our backpropagation algorithm, which uses dynamic programming, so we're not going to have any exponential computation. But that's the idea of the skip connection. So the skip connection has a derivative 1 and allows then an easy way to get gradient to early layers. And this works so well that Resnet can be extremely deep, right? We've seen, for instance, Resnet 34, but it's really a whole family. So that we have 34, we have 101, we have 152, all of which work very well because the training works well because we have this way to get gradient back to the early layers. So unlike, let's say, Inception, where they had this problem of doing the training of the early layers, where they added these extra classifiers, these temporary classifiers, instead, we can just do our traditional classification in our output layer, compute our loss with respect to any of these weight matrices. So now we've got to talk about how this skip connection actually works. And that's where we're going to get into this idea of residuals. So a residual is just a fancy name for leftover. My kids always used to say, "Oh, Dad, do we have to have residuals for dinner again tonight?" They actually didn't do that, but they could. So residual just means leftover. So let's look in more detail how a skip connection is actually going to work. First, let's just say we have some y. We can go ahead and rewrite that if we want as y equals x plus some h of x, where h of x is what we're going to call the residual. Right? If we look at this, basically h of x is just equal to f of x minus x. It is the residue, or the residual, of f of x with respect to x. And that's what we're going to do with our convolutions. So our convolution layer, we're going to take x coming in. We're going to also take x and go around the convolution layer. And we are going to combine them with a pointwise addition. So the output is equal to the input plus h of x, which is the residual, which is the computation of the convolution. So the convolution is no longer responsible for computing the final value. Right? That's how it used to be, where we would just have x, go to a convolution, go to the output, go to the next convolution. Here we're saying, convolution, your only job, instead of coming up with a final result, I just want you to come up with what is the difference from x. So how should the output be different from the input? Okay. What is the delta? So that's the convolution is supposed to calculate the delta between our desired output and our input, rather than just computing the desired output directly. So if we look at this then, we look at our, right, z was equal wx plus b. Now what we're saying is z, our output of this layer, is going to equal x plus wx plus b. And so when we look at the derivative of z with respect to whatever our input is, right, let's just say x is the output of the previous layer, right, it's no longer going to be w. It's going to instead be 1 plus w, roughly, reflecting the fact that we get a 1 here and then a w going through the convolution. So two different paths, so we add them together. One path is the 1 here, one path is the w here. So that is how we are going to do our layer here. It's slightly different actually. In Resnet, they don't have a skip connection around every convolution. Instead, what they actually do is run two convolutions together. They have one convolution, they have another convolution, both of these have values in them. And so our input will skip around two convolutions instead of just one. Like almost all convolutional networks, there is this shrinking of the height and the width as we go through the network. So we're often reducing our h and w dimensions and increasing our d dimensions. The question is, how do we reduce the h and w dimensions? It's easy to see the increasing the d dimensions because it's just the number of convolutions, right? The number of kernels controls the depth. So we need to ensure that we have our input here and that our input matches the shape of the output convolution. So we've got to do two things. We've got to make sure the depth matches, and we've got to make sure the height and the width matches. Well, as long as we're not shrinking the height and the width will be maintained. X, of course, has its height and width, and as far as these convolutions are as long as these convolutions are half padding and one stride, then the height and the width are going to be the same coming out of these convolutions as they are going into the convolutions. So those will be compatible as far as the height and the width. Let's see about how we're going to deal with the depth. So let's say we had something of size 50 by 50 by 32, and we're going into some convolutions that maintain the 50 by 50, but there are 64 of these coming out. So that means the size of this is 50 by 50 by 64. So we need to make sure we're compatible. There are two things that can be done. So one thing that can be done is we can go ahead and pad with 0. So that'll take the 50 by 50 by 32 and just convert that to a 50 by 50 by 64. And that will then be compatible with our addition here. So we can do 50 by 50 by 64 and 50 by 50 by 64. That's one option. The second option is to go ahead and feed this into 1 by 1 by 32 convolution, and we have 64 of those. That would also generate an output of size 50 by 50 by 64. Either of those will work as a way of adjusting the depth of X, as we are normally just kind of keeping it as identity, but if we're changing the depth through our convolution path, we need to also change the depth through the identity path. So we can do that either by padding with zeros or by going ahead and using 1 by 1 convolutions. So each of these convolutions is basically going to just say, how do I take a core of 32 values and turn it into a single value? So the 64 of them will each independently decide how to take these 32 and combine them into 64. There are also some shrinking in size. So the shrinking of dimensions isn't done with pooling. Instead, the shrinking of dimensions, so if we have 50 by 50 by 32, and we want to end up with 25 by 25 by 32, what we do is actually go through and use convolutions. Don't use any max pools. So instead, we can take a convolution. If we have a 3 by 3 by 32 convolution, and we have 32 of these, how can we get from 50 by 50 to 25 by 25? Well, that's simple. We just make sure we use a stride of 2 instead of by 1. If we use a stride of 2, then that will go ahead and go from 1, 1 to 3, 3 to 5, 5, centered there. And so we're going to cut this down by a factor of 2. So the Resnet, no max pools, instead it just uses a stride of 2. If it's going to go ahead and use a stride of 2 in one of these convolutions, then that's going to reduce the dimensions, the height and the width coming out here. We'll have to similarly reduce the dimensions coming out of here too. Okay. The simplest thing to do for that is we can go ahead and use a 1 by 1 convolution, same 1 by 1 convolution again with a stride of 2. Okay. Alternatively, what we could do is just skip every other pixel. That would work as well. That's kind of the analog to doing this padding by 0. Just skip the pixels. But we could go ahead and use 1 by 1. How many of them would you have? Be 1 by 1 by 32. We'd have to have 32 of them to match the 32 here. So we just have to make sure everything matches. So Resnet introduces the idea of skip connections. These skip connections are calculating residues where each convolution or this convolution pair is, instead of computing the actual output it needs, just computing a residual from the difference of x. One thing to look at is that it's very easy for this network to turn on and off certain of the modules here, right? If it set these weights and bias to 0 and these weights and bias to 0, this would basically be a no-op, right, as we go through here. And so if we have k different of these blocks, these skip blocks, it would be very easy for the network to decide which of those k blocks it wants to actually use and which it doesn't use. So if we imagine we have 3 blocks that can be skipped, right, 1, 2, and 3, and we have skip connections around each one of these, then we can compute either, right, so we have our input coming in, and we can go through 1 and then go to the end. Or we could go through 1 and then 2 and then go to the end. Or 1, 2, and 3 and go to the end. Or we could go directly to 2 and to the end, or to 2 and 3 to the end. Or we could directly go to 3 and then the end. Or theoretically, we could just go directly to the end if we're trying to compute the identity. So we've actually got 8 different paths through here that we can take, depending What I mean here is if 1 is actually computing nothing, computing 0, then we're getting the effect of going through 2 and 3 that are non-zero. So depending on whether 1, 2, or 3 is computing 0 based on its input, then we've got, in effect, 8 separate sub-networks in here that the network can learn. So it's got 8 different network architectures that it can build from this one single architecture. It can compute architecture where 1 is producing nothing, right, just generating 0, and then it's doing 2 or 3. Or it can have 1 and 2 producing 0 and just doing 3, or 1 and 3 doing 0 and just 2. So it's got this large variety that it can use, and in some sense, it can go ahead and figure out exactly how long a network it really needs, because it can just easily shut down parts of the network that it doesn't need as it's learning, right? This is not something that happens during execution time. Although actually there was an interesting paper that looked at a trained Resnet and then said, okay, what happens if we just disable certain of these blocks, just have them produce 0? And it turns out, as you start shutting down more and more of these, the error rate gradually started increasing very nicely, so that it scaled kind of nicely to these blocks. That's ResNet.